Okay, I guess there are no questions for now. Let's start. So in the cross-sectional data chapter, we have discussed the different microscopic single vehicle data as well as the macroscopic data that is provided by the detectors directly. So in the microscopic single vehicle data, we have information about the length of the vehicle, the time headway, delta TI, not to be confused with delta T, which is the aggregation interval, then time gap, distance headway, and distance gap. These are all the single vehicle data that the detectors can provide to the traffic control center, but usually to save bandwidth and the disk space, it does not. What it does is it aggregates the data and then send it over fixed time intervals delta t. And please let me know if you are unable to see the screen. I'm sharing my screen, but if you're not seeing it, please let me know. So the aggregated data that it sends is traffic flow, and it also shows us that there's a correlation between what is called as microscopic flow and the traffic flow. The microscopic flow is defined as the reciprocal of the time gap, delta ti, or I should say the time headway. And the relationship between the traffic flow and the microscopic flow is provided in equation 5.8, where we have 1 divided by the average of reciprocal of microscopic flow, or 1 divided by the average of all the time headways that we have obtained from the detector data. The next thing that sends is occupancy, which is the fraction of time that vehicles were observed on the detectors. Arithmetic mean speed is another thing that detectors directly send. But in the chapter, they say that harmonic mean speed, arithmetic time mean of the microscopic flow. This is, remember, not the main traffic flow, but the microscopic flows mean. And then the speed variance. These are the things that are very useful, but they are either sent or not sent depending on the type of detector and software the company is using or the city is using. So this is where we stopped our discussion the last time. Today we are starting with estimating spatial quantities from cross-sectional data. So our main goal in this section is to determine traffic density because we cannot directly determine it from the detectors. We do know flow, we do know about arithmetic mean speed, but we do not know about traffic density. And as we know so far, traffic density is one of the fundamental quantities that we need for our later analysis. So traffic density is redefined here. It is defined as a spatial average at a fixed time, the number of vehicles on a given road segment. And because when you're using just a single loop detector or even double loop detectors, we need delta x. So we need a space interval during which we could be able to estimate the traffic density. And those detectors generally do not provide that information. They are at a fixed location at a cross section. So that's why flow is available, but traffic density is not directly available. But we can use existing equations, our existing understanding, which was previously told to us using the equations of the time mean speed, equation 2.5, and equation 2.6 is the space mean speed. And then the Eddy's equations. So Eddy's equations are right here. Here, the density is defined as a total travel time of all vehicles within a spatiotemporal region A. But remember, we are dealing with cross-sectional data, where we do not directly have the spatiotemporal region A. We need to define what A is, given the context of the cross-sectional data. And then we also see that the speed here is the total distance traveled by all vehicles in A divided by the total time traveled. And that using the hydrodynamic relation, we have Q divided by rho. And based on that, we can determine rho using Eddy's equation only if We have the q as an eddies from the eddies equation as well as the speed from the eddies equation. But keep in mind that the speed that detectors send us is not the eddy's speed. It is the macroscopic speed, which is the arithmetic time mean speed, different from eddy's definition. Previously, we have also discussed this equation from the Lutz-Bach relation, where the time mean speed is found to be always greater than the space mean speed because it includes the variability in the speeds as well. And time mean speed and space mean speed would only be equal if the speeds of all vehicles is the same. Otherwise, there will always be a difference. And here there's a typo that I highlighted. It says that space mean speed is always greater than the measurable time mean, which is not true. It is always smaller than the time mean. Another important thing here, which is a definition of stationarity in the statistical sense. So here's what stationarity in statistical sense means. It is that the vehicle speeds can vary, but the distribution function of the speed variations at a given location does not change in time during the aggregation interval. So to take an example, let's say our aggregation interval is 15 minutes. That's delta t. Within those 15 minutes, we know that the vehicles that pass a detector are going to have different speeds. So we get all those speeds and we create a distribution of it. If this distribution of speed, which means if it is parameterized by a Gaussian distribution with a mean and a standard deviation, if those parameters are not changing over time, and by time I mean only this aggregation interval of 15 minutes in this example, then we say that the conditions are stationary in statistical sense because the distribution function remains the same within the aggregation interval. After 15 minutes are over, maybe the distributions change, maybe the mean or standard deviation change, but within that delta t, it does not change. So in that case, it would be stationary conditions. We know that when they are stop and go conditions, then those are not stationary because even within those 15 minutes, some of the vehicles would be moving, others would be stopped, and so their mean would change even within 15 minutes. So those would be non-stationary conditions. So our goal in this section is to determine traffic density, and this is why we are defining these relations again from the previous chapters, just to remind ourselves what is the time mean speed, what is the space mean speed, and we need that because we want to use this relationship. Density is equal to the flow divided by the speed. But this is only applicable if we can use Eddy's equations or if we can use Vs instead of V, which is the the space mean speed. We cannot directly use the time mean speed here because otherwise it will be a biased estimation of the density. It also mentions here that the harmonic time mean speed Vh is approximately equal to the space mean speed. So if we could get space mean speed, we can then use the hydrodynamic relation here and estimate traffic density. So in this next section, we are estimating the space mean speed first. Once we get that, then we can use the hydrodynamic relation. So the example is about this scenario. And if I'm going too fast, please let me know if there's anything you want to discuss before we go to the next point. Am I still sharing my screen?
Right now, we are not able to see your screen.
Okay, let me reshare.
Now it's good.
Okay, thank you. So in this example, we have two lanes. On the right lane, we have these two vehicles, including the detector area. So it's from the beginning until the detector area, we have these two vehicles which have a speed of 72 kilometer per hour, both of them. And then in the left lane, we only have one vehicle which has a speed double of the right lane speed, which is 144 kilometer per hour. So all vehicles in left lane will have the identical speed of 144. The space headway between them is 60 meters in the right lane and twice in the left lane, which is 120 meters. So given that information, what we want to do is estimate the space mean speed. So here they mentioned that the time headway can also be estimated here using the space headway divided by the speed. So for example, if the space headway is 120 and we have the speed of 72, then 60 and 72, then we can estimate the time headway based on that. So using the equations of the time mean speed and the space mean speed and the harmonic mean speed, we can estimate these values. So the time mean speed is simply the arithmetic average. We have B1 from right lane. Here they mentioned the lanes. Lanes are L1 and 2. One is right and two is left. So V1 is from the right lane, V2 is from the left lane. So we know those are 144 and 72, and we take an average that comes out to be 108 kilometers per hour. Then the space mean speed is considering only this area. Within this area, we have 60 meters of the space headway in this lane, and we have 120 meters in the other lane. And what we want to do is we want to look at these vehicles in each lane. We know that there's a total of three vehicles. So we have actually we're looking at this complete area, and we are looking at what is happening in front of this follower. So this follower has this leader, and then this follower has this leader. So we have um, one and two vehicles in right lane, and then one vehicle in the left lane. So a total of three vehicles. Out of those three vehicles, there are two vehicles in the right lane, these two, and one vehicle in the left lane. That's why we weight each speed, each lane speed based on that. So 2 into V1 and 1 into V2. Based on this, we estimate the space mean speed and we get 96 kilometers per hour. If we use the formula of harmonic mean, it is 1 divided by V1 plus 1 divided by V2 and then divided by 2. And we get the exact same 96 kilometers per hour as we got for the space mean speed. So we show here that space mean speed is equal to the harmonic mean speed. And now the area is also defined. A is equal to delta x into delta t. Delta x here is a total space of 120 meters, which is between this vehicle and the front of this vehicle. That's 120 meters. And delta t is the aggregation interval. So based on that, and from Eddie's definition here, we are now estimating in the stationary conditions what would be the space mean speed. So that would be equal to the eddy speed, which we can then estimate based on the total distance traveled and total time traveled. So total distance traveled, the numerator remains the same throughout this derivation. The total time traveled is based on tau I. Tau I is the travel time. This is the travel time inside the region of the vehicle I. So for vehicle number one, it would be tau one, and then we sum all those travel times. Here it shows that lambda is also defined here, denotes the distance that the vehicle I travels inside the spatiotemporal region underlying ID's definition. So this is the distance traveled by the vehicle, which obviously goes from the minimum x coordinate up to whatever x max is, and that we can get from x min plus lambda. So we are integrating the slice of distance that is covered by a vehicle I divided by its speed at a given location x, and we're integrating it for all x values. So essentially getting the total time traveled. That comes out to be delta I divided by Vix. So this equation is the equation for the space mean speed, which we started with to estimate for the stationarity conditions, which means that the conditions are not changing over time. The speeds, the distribution function of the speed remains the same. So based on that, we define the stationary space mean speed. And then later, it is also shown again that the space mean speed comes out to be equal to the harmonic mean speed. So if we can estimate or get from the detector data the harmonic mean speed, then we are able to directly use the hydrodynamic relation of rho is equal to q over v. And for v, we would use the harmonic mean speed. So the main takeaway in this section is while the approximation is generally robust against violations of the stationarity, it breaks down when aggregating over jam fronts or inside stop traffic, which means that as long as the conditions are stationary conditions in statistical sense, we are good with using the hydrodynamic relation, given that the speed is not the time mean speed, but the harmonic mean speed or the space mean speed. In the next section, we are now estimating the traffic density. But any questions for this section, please let me know.
Uh, my question is regarding the definition of stationarity.
Okay.
So, uh, uh, if I remember it correctly, you said that we have the mean and distribution for the speeds, all of the speeds. And then, I mean, it would make sense if you are comparing one in 15-minute interval to another 15-minute interval. But I think that's not what you said. You said that even if the values are changing within the interval, then the condition is not stationary. So that is a bit confusing to me.
Yeah, so based on what I understand from the chapter, what they're saying is we take an aggregation interval, as you mentioned, 15 minutes. So let's take delta t equals to 15 minutes. And within that 15 minutes, if we see that the distribution of the speed changes, then the conditions are not stationary. Which means, for example, within those 15 minutes, we can see for every 5 minutes, what is the average speed and what is its standard deviation. That will, assuming that the normal distribution is a good approximation of speed distribution function there,
Mhm.
then those are the two parameters only for normal distribution that tell us what is the
Yeah.
distribution. So the
Yeah.
mean and standard deviation for the first 5 minutes, then for the next 5 minutes, and then for the next 5 minutes in the total of delta t. If we see that the mean and standard deviations are not varying significantly, then we say the conditions are stationary. But if we see that they are significantly changing, which can happen if there's stop and go conditions. So let's say in the first 5 minutes, no vehicles were stopped, but in the next 5 minutes, some of them vehicles were stopped. That would decrease the average speed. So that would change the distribution itself, right? So
Yeah.
within
Yeah.
those
I mean,
15 minutes, yeah,
yeah. So I mean, we still need to divide that 15 minutes into smaller chunks to get different values of mean and standard deviation. So
right. Yeah, that's
yes.
how I am understanding it. Yes.
Yeah. Yeah. That's correct. Okay. That's fine. Let's carry on, please.
Okay, thank you. So now we are going to discuss traffic density. So as we discussed before, we have this hydrodynamic relation of rho, which is traffic density, equals to traffic flow Q divided by the space mean speed or the harmonic mean speed, as we discussed in the previous section. So based on that, they provide this other symbol, P or rho tilde, to uh, to represent the estimate of the traffic density, when we are using harmonic mean speed. Theoretically, the actual relationship is rho is equal to q over v, this thing. But with detector data, we cannot use v directly. We need to depend on harmonic mean speed. But it says here that unfortunately harmonic speed is generally not available. Okay, so then what do? We then use the time mean speed, but then this is an estimate, and this estimate is represented by rho hat. And because of that, we are going to get some bias, which means that we are going to get an underestimation of the true density. Why underestimation? Because we know that from the Lutz-Bach relationship, the time mean speed, this thing, is always going to be greater than the space mean speed. So if this value is greater, that will reduce the density, and so it is underestimating the true density. So using that relationship again, here they prove, actually quantify the quantity of bias. So this is based on this equation 15, 5.15, where we're using the space mean speed and this is using time mean speed. So we are getting the amount of bias that we get by comparing these two equations. So here's an example from figure 5.4, this figure again. So here they say the true density over both lanes is given by this, which is that we have three vehicles divided by 120 meters. Three vehicles because we have between the front of this vehicle and the front of this vehicle, the space headway is 120 meters. Within that 120 meter, in the left lane, we only have one vehicle. We are not counting the one here because it's starting from the front of the vehicle. And we have two vehicles in the right lane, a total of three vehicles. So those are 1 plus 2, three vehicles divided by 120 meters. That comes out to be 25 vehicles per kilometer. That's a true density. Now, using the relationship between the traffic flow and the microscopic flow or the space headway, sorry, the time headway, delta ti, if we get all the time headways and we take an average of that, that is the expected value of delta ti. And if we take a reciprocal of that, that is equal to the traffic flow. So based on this formula, we get one vehicle divided by 3 seconds. And where is 3 seconds coming from? 3 seconds is the time headway. The time headway is again based on this information that the space is 120 meters and the speed is 144. Using the distance and speed, we can estimate time. So converting it to the units of meters and seconds, we get one vehicle per 3 seconds in the left lane and one vehicle per 3 seconds in the right lane. Because the time gap does not change, the space headway, sorry, the time headway does not change in the two lanes. And that comes out to be a total of 0.667 vehicles per second of traffic flow in both lanes. So based on that, we can now use our formula from equation 515 and 516. So with 516, we get 22.2 vehicles per kilometers. And with 515, we get 25 vehicles per kilometer. So we can clearly see that this is an underestimation of the true density, which is 25. But this is a very good approximation of the true density. In this case, we get an identical answer using the space mean speed. So 25 equals 25 here. Here they say the bias can be understood by observing that in relation to their partial density, faster vehicles are seen more frequently by detectors than slower vehicles, yielding a bias towards larger speed values for the arithmetic mean. So if you're using 516 equation here, that is using arithmetic mean, it means that faster vehicles will be observed more, and so we are underestimating the true density. That's why P tilde or rho tilde is a better approximation of the true density. Okay, any questions before we go to the next section? Okay, in this section, we are now discussing traffic density for non-stationary traffic. What we have discussed here, this is for stationary traffic only, which means that for non-stationary, we are going to consider stop and go conditions. So the first subsection here is the derivation from the expected value of traffic density. So if you look at equation 5.4, this is the distance headway, which we have previously discussed. It's equal to the speed of the lead vehicle into the space headway delta di. Based on that, and based on the definition or the relationship between density and the distance headway, we get this, that the density is correlated with the distance headway's arithmetic mean. We take all the distance headways from the vehicles, take an average of it. The reciprocal of that is going to be the traffic density. This is equivalent to the relationship between the traffic flow and the time headway. So based on that, they derive this equation. Rho is equal to Q or V, as we know before, but now this part is added. We are considering rho hat, which is using the time mean speed, into the covariance between the speed and the time headway. So let's discuss the speed and the time headway. And we have two conditions. We have free flow conditions and we have congested conditions. In both of these conditions, what do you think is going to be the relationship between the speed of a vehicle and the time headway that it is keeping from the lead vehicle? Let's start with the free conditions. So what do you think will be the relationship between time headway and the speed of the vehicle in free conditions? Do you think there is a correlation there? What do you think, Sabah?
Yes, I think there is a correlation.
Is it a positive correlation or a negative correlation?
Negative correlation.
Do you think if there is a higher time headway, then the speed will be lower? Or if they are, I should state that in the opposite manner. So if the speed is higher, then the time headway will be smaller?
Yes, I think.
Uh, can I add?
Yeah.
I'm not sure, but this is like a wild guess. I think when the vehicles are moving at a higher speed, they will also tend to maintain a larger distance, and when the speed is lower, they will tend to come close to each other. So I think average, the time headway should remain around the same.
Yeah, on average, I agree that it should remain the same. But when we only look at the correlation, I also tend to agree with you, Asan, that the at a larger speed, you would tend to keep a higher time headway. But let's think about free conditions only, when you can go at your desired speed. So you're going at, let's say on a highway, you're going at 115 kilometers per hour, right? And it is free conditions, so the lead vehicles and the following vehicles are farther apart. In that case, I think there will be almost no correlation because you rarely see a lead vehicle. So you're not really affected by the lead vehicle. You're just keeping whatever time headway you want to keep, depending on your desired speed. So those are really free conditions. But as you go from those conditions to relatively less free conditions, and then ascent, like essentially to congested conditions, Then, as you are slowed down a lot, as you're slowed down a lot, I think in that case, it will take you more time to get to the same detector that the leader had previously been to. So that would take a longer time. In that case, I think the correlation would be positive. So what do you think? I think in free conditions, almost no correlation. In congested conditions, a positive correlation. Let's see what the chapter says. So
Yeah.
based on this, so we have covariance, and then they later uh, talk about the correlation instead of covariance, which is defined here in equation 5.22. And so now they've given us something new here, which is called as Wardrop's equation, equation 520. And equation 523 is now using the linear correlation R between the speed and the time headway instead of the covariance. And so here is the description from the chapter. It says the real density equals the widely used estimate flow divided by arithmetic mean speed, which is this part, multiplied by a correction factor that captures the correlation between speed and headway. So this part in the brackets is the correction factor. And it's also considering the linear correlation as well as the relative variance of the vehicle speed and flow. Sigma v divided by v, this is the relative variance of vehicle speed and flow. And the dimensionless product uh, q into sigma delta t of flow and the standard deviation of time headways. There's a lot that they have covered in this correction factor. Now here's the explanation on the free traffic. In free traffic, the linear correlation R is near zero since every driver is able to choose his or her speed independently. So because they are going to their desired speed, there is essentially no correlation between their desired speed and time headway because they can go at any speed they want, and they don't really care about what where lead vehicle is. In congested traffic, however, the headway delta Ti usually increases with decreasing speed, and tends to infinity as the speed approaches zero. So here I was wrong. This is inverse correlation. So in congested traffic, headway delta Ti usually increases with decreasing speed. So as you are slowing down because of, let's say, stop and go conditions, you are slowing down, your time headway is going to increase. And that is because you are slow. You're moving very slow. So you will take more time to get to the detector compared to the time when the lead vehicle got to the same detector, because that is how time headway is estimated. The lead vehicle enters,
Vehicle entered.
crosses the detector first, and then you as a follower cross the same detector. The time difference between them is the time headway. So because you're slow, you're going to take more time, and then essentially delta ti will increase when you are slow. So there's an inverse correlation here. So therefore, the correlation is negative in this case, and the correction factor is greater than 1. Thus, relation Q over V is biased and systematically underestimates the real density in congested traffic. If we only use Q over V as we were using for stationary conditions, it is going to be very biased. So it's not a good idea to do that. That's why we need to use this correction factor also. Um, Anything you'd like to discuss?
No, no, nothing.
Yeah.
That's, you know.
Let's continue. So then they do another approach where it's derivation from the expected value of traffic flow instead of what we discussed above was based on the expected value of traffic density. So we have previously seen this relationship between flow and time headway. Based on that, they come up with this derivation. Again, rho is equal to q divided by v superscript h, which represents harmonic mean speed, which represents the space mean speed. And we saw that in stationary conditions, this is enough for us to get a good estimate of traffic density. But now we use the correction factor because, again, these are non-stationary conditions. And that's essentially equal to rho tilde because q over vh is rho tilde, and with the same correction factor. So here it says q over vh. If we only use that without the correction factor, then it's going to overestimate the real density. So it is a good idea to use that correction factor. And here's a discussion of the two approximations. In practice, they say here you are limited to use Q or V or Q or VH. People don't use correction factors as per the description here. And here they say the following statements help in assessing the errors of the two estimates. If all vehicle speeds VI are the same, then the time mean speed is equal to the harmonic mean speed, which means that all estimates of density are equal, so we are good. If all headways delta Ti are the same, then the covariance is 0. And then rho, which is the true density, is equal to the rho hat, which is Q over V. Otherwise, rho hat will underestimate the density as we saw before. And similarly, if all distance headways are the same, then rho is equal to rho tilde, which is Q divided by BH, and it's going to overestimate the real density. So if we use only these equations, then we do get an approximation of the density, but they will either overestimate or underestimate the density. This is the limitation. So if we can use the correction factor, that will give us a better result. But obviously for that, we need to know what is the correlation. And if we don't have data for that, we cannot use the correction factor. We need to either assume it or just use these equations. All right, next section is determining the speed from single loop detectors. In the beginning of the chapter, it mentions that you cannot actually determine speed from single loop detectors because single loop detectors have a very small distance between them. The spacing is very small. And so even if you use double loop detectors, if we have a distance of, let's say, 2 meters, in that case, it makes sense because you have some distance and speed estimations require you to have some distance. So double loop detectors will give you the speed, single loop detectors won't. But here they say that if we assume an average vehicle length, so from some previous data, or if we just make a reasonable assumption about vehicle length, then we can use the formula of the occupancy to determine the speed. So they derive this equation for the occupancy, equation 5.29, where the harmonic mean speed is equal to the flow into the average of the assumed length of all vehicles and occupancy multiplied with, again, here this is traffic flow, occupancy, and the covariance between the length of the vehicle and the reciprocal of the speed. Obviously, if you have trucks and cars, trucks have a longer length, but they generally have a smaller speed. So definitely there's going to be some covariance between these two variables. And here they say for all these cases, the traffic density can be easily estimated as well. So if you have single loop detector only, and you have a reasonable assumption of the length of the vehicles, then you can use this equation for determining the harmonic mean speed. Or you can use this equation also based on our previous discussion, where we have harmonic mean speed coming from traffic flow and the estimate of traffic density using VH. And we can then determine the traffic density using occupancy and the length of the lead vehicle, sorry, length of all vehicles. This is the average of all vehicles length. So using either equation 529 or 530, we can estimate harmonic mean speed and also density. Okay, next section is the last section in this chapter, but this is a very long section, and we have only covered, I think, two sections. Yes, so two subsections in this. So at least I have only read until that. So we are only going to cover to this part, and I think we need to discuss in next two sessions the rest of the chapter and the exercises. So let's wrap up today's discussion with these two subsections, which is about analysis of cross-sectional data. The first part is about desired speed distribution. If you have used PDVSim or any traffic simulation software, they generally ask you to provide a desired speed of the vehicles or a distribution of the desired speeds. So this is where we understand how can we use detector data if available to get desired speed distribution. And once we have that, we can then use it in our simulations. So for desired speed distribution, excuse me, we need single vehicle data. We cannot just use macroscopic data, which is aggregated by the detector. We need to use single vehicle data of low density traffic because we are talking about desired speed. So here's an example. In this example, this is from a paper cited here. And in this example, we have three lanes on a German highway, and we have the left lane, middle lane, right lane on the plot here. On the x-axis, we have the speed in kilometers per hour. Actually, let me increase the size here so it's clearly seen. And on the y-axis, we have the probability of the speed, essentially the speed distribution. And the legend here tells us the density, but look at the units. The units are in percentage. So looking at the paper, this is not actually traffic density. This is density estimated from occupancy. So I think they have done something like this, where they have used occupancy, and that's why uh, this is reported in percentage. Since we are talking about free flow conditions, we have two conditions where they estimated the distributions. One condition is 0 to 5% of occupancy. The second condition is 5 to 10% of occupancy, which is telling you that there are not a lot of vehicles detected by the cross-sectional detectors. And so they're only about up to 5% or up to 10% of occupancy. So based on that, we are now looking at the speeds. So if you look at this one, the circles representing 0 to 5% of occupancy, in the left lane, we clearly see that the mode here is almost 150 kilometers per hour, a pretty high speed. And then in the second distribution, this is for 5 to 10% of occupancy. Obviously, now there are more vehicles, so a slightly less speed. But this is still pretty high. It's about 130 kilometers per hour for left lane. For middle lanes, the speeds are, or at least the averages of the speeds are a bit slower. And in the right lanes, we have the slowest speeds. And we also see in the middle lane, at least for this distribution, there are two modes. There's a mode here and a mode here. And in the right lane, we see two modes or bimodal distributions for both of these distributions. So one mode is here, another mode is here for 0 to 5%. And for 5 to 10%, we have one mode here and another mode here. So these bimodal distributions represent two different classes of vehicles, trucks and cars. For cars, the speeds are higher, so those are here. And for trucks, the speeds are smaller, so those are here. And trucks generally do not use the middle and the left lanes. That's why we see that bimodal distribution in right lane only. Okay, so in the second figure here, figure 5.6, we see on the x-axis the density for a given lane. So this is vehicle per kilometer per lane. And on y-axis, we have the difference in the average speed right here. It's a difference in average speed between neighboring lanes. And the black line here is telling us about synchronization. If the difference in the average speed of the neighboring lanes is zero, right here, that tells us that the speeds have synchronized. All lanes have the same speeds. The red circles here represent the difference in average speeds of left and right lanes, and the blue circles here represent the difference in average speeds of middle and the right lanes. So as we have a smaller density, which means more free flow conditions, the difference between left and right lanes and the middle and right lanes in terms of speeds is higher. But as you go to higher densities, they also synchronize sometimes. Yes, there are some higher differences or lower differences than zero, but we see mostly they're around the zero average speed difference, which indicates that they synchronize at higher densities, which is expected. So here they say that the average free speed V naught is when the density approaches zero. When density is exactly zero, at that time, obviously, there are no vehicles to be observed, so there is no speed. But as it approaches zero, as we go to the left of this plot, we are getting what is called as the free speed or the desired speed. And in the final subsection for today, we have the distribution of time gaps. So here's the plot for the time gaps. We see two distributions. On the x-axis, we see time gap. On the y-axis, we see relative frequency. So this is the distribution of the time gaps in two speed regimes, free and congested traffic. Free speeds are defined here as speeds which are higher than 60 kilometers per hour, so the blue plot, and the congested conditions are speeds of less than 60 kilometers per hour, the red plot. If you look at the mode of the time gaps here, we see that it is around 1 second. So I would say this is about zero point 0.9 seconds for the free conditions and about 1.2 seconds for the congested conditions. So this is a very small time gap. And here they mention that it is not unusual to see standard deviations larger than the arithmetic mean of these distributions. We see that they are asymmetric distributions. They are not normal distributions. We have a longer right tail, and the reason is that these are we are getting these from the data, right? These are from conditions where speeds are more than 60 kilometers per hour, but even 60 kilometers per hour, especially on a motorway, remember this is from motorway data, 60 kilometers per hour is not a very high speed on a motorway. So it still includes some, I would say, relatively congested conditions in the free regime plot as well. And so this is the upper limit of these time gaps. The lower limit would be very small. The desired time gaps that people want to keep would be actually much smaller than what we observe here. And this is indicated, actually, this is mentioned by the chapter. In both speed regimes, T cap, or the mode of the time gap, is significantly smaller than the recommended safe time gap. So they provide the definitions for US and for Europe. In Canada, there's also a definition to keep a 2 to 3 seconds of difference from your lead vehicle. But here we clearly see that it is around 1 second. So it's much smaller than what is recommended. They also mentioned that in free and congested traffic, we observe time gaps longer than 10 seconds also. Okay, and here they mentioned that traffic jams usually do not dissolve quickly once they have emerged, and that is because of the capacity drop. That capacity drop is the flow decrease after a traffic breakdown. And that is indicated by the longer tail, the right tail of these time gap distributions where we have 5 or 6 seconds of time gaps. Most of the observed time gap distributions are not identical to the distributions of drivers' desired time gaps. As I mentioned before, this what we see here is just the upper bound. These are not representing the smaller desired time gaps that people would actually keep if they can. All right, I think that is it for today. Um, any questions? So I'll quickly add one equation to our package here for chapter 5. Let me share my screen and then we'll wrap up for today. For some reason, it's not allowing me to share my screen again. Okay. Um, okay, I'm going to join in a second again. I'm going to come back. Can you see my screen?
Yes.
Yes, yes.
Okay, good. All right. So here I added this file Ch05, and this is just a single equation that I added so far. So we have multiple equations here in this chapter. I think we don't really need everything. So I added this equation for microscopic flow. So the way to add this equation, and if someone is interested, you can also make this contribution. Go to GitHub and then um, add these equations whenever you can. So with the add equation function, we can provide the key microscopic flow, which is essentially the name as well. But this is easy to use in the show function. And then this is for chapter 5. This is 5.7. And this is the latex in raw format for that equation. And now if let me restart my session and then import the package. If we now look at list equations, currently we only have two. Traffic density equation from equation 2.1, chapter 2, and microscopic flow, this one. And now if we look at this one using the show equation, so show function, sorry, and provide it microscopic flow, then it shows us this equation as a mat.lib output. But I'm thinking to also add the definitions of these things because this is not clear just by looking at this equation what each of these terms mean. We know this is microscopic flow, but we need to define this as well. So I'll add the functionality to do that. Any questions? Okay, all right, then I'll see you next time. We hopefully will have 2 more sessions for this
Thank you.
this chapter. Thanks a lot. Take care.
Thank you. Thank you. Bye.